this video, an ENACT coach will model 2 strategies teachers can use to support students in taking ownership of computational thinking practices. We call these strategies prompting and pointing out. The coach will model how you might prompt students to use computational thinking by making suggestions about how students can use CT practices to approach a problem. Then the coach will model how you could point out when you observe students using CT practices, whether they realize they were doing so or not. The examples in this video focus on finding surface areas of 3-dimensional figures. Students are exploring surface areas of boxes they plan to submit to a contest sponsored by a packaging company. But the ideas in this video could be adapted to align with any problems about surface area. Let's watch an example of the coach prompting students to use algorithms. The class is getting ready to find the areas of rectangles and triangles, and the coach prompts them to think of the area formulas as algorithms.
You're doing a good job finding all the dimensions of the faces. I noticed a lot of you are writing the dimensions right on the picture, which I think is a great idea. Your next step is going to be to find the areas of all the faces. How are you planning to do that? I know these are on grid paper, so one strategy you could use is counting the squares to find or estimate the area. But since you're already writing down the dimensions, another idea is to use the area formulas. Area formulas are like algorithms because they show you step by step how to find the area if you already know the dimensions. If you use the area formula, you'll get more practice using algorithms, and it might also be faster and more accurate than if you count squares.
Another video in this collection provides a more detailed example of how you can help students connect formulas to algorithms. Now let's watch as the coach prompts students to use abstraction to help them focus on the important parts of a problem.
Part of your challenge for today is going to be to decide which of these packages to submit to a contest. So a packaging company is having a contest to decide what package to use next, and they ask 6th graders to submit ideas. So what's important to consider when you're choosing a package? Maybe we can use abstraction to help us think about this. Abstraction helps us focus on important information. So what's important to consider when you choose a package? I know that if I worked at the packaging company, one thing I'd be interested in is how much material is each one of these packages going to use. So maybe you can talk about that with your group. How could you figure out how much material each one is going to use? What else might be important to consider when you choose? Yeah, that's a good point. Probably the packaging company is going to want to know what they can fit inside each of these packages. So that's another thing to think about. How could you figure out what can fit inside each of these? Keep talking with your group about what might be important to consider when you choose a package, and then you can use that to make a list of advantages and disadvantages for each option.
The coach just prompted students to use abstraction, giving them examples of how they might identify important information in the problem they were solving. Now let's watch as the ENACT coach is pointing out how students developed algorithms as they solved surface area problems.
Part of your task today was to find a general method for finding the surface area of any box. Let's take a look at some of the general methods groups came up with. So here's one example. Method 1 says, you can find the surface area of any box by finding the areas of each face and adding them up. Thumbs up if you agree with that method. Does it seem like it would work? Is there anything we could add to it to make it clearer or more complete? Okay, let's look at another example. So method 2 says, step 1, find the areas of all the rectangle faces. Step 2, find the areas of all the triangle faces. And then step 3, add all the areas of the rectangles and triangles together. Thumbs up if you agree. Does that method work? Anything we could add to make it clearer or more complete? So Sam said something really interesting that I want us to think about. Sam said, I think when we're finding these general methods, we're writing algorithms. Do you all agree with that? Let's think about that for a second. Talk with a partner about whether you think our general methods are algorithms and why or why not. Okay, Sparrow, can you share what your partner said? All right, so your partner thought they were algorithms because they give step-by-step instructions for finding the surface area. Okay. And Nikki, how about you? What did your partner say? Oh, okay, that's interesting. So your partner thought maybe method 1 wasn't an algorithm because there are no steps. You're right that there isn't like step 1 and step 2 labeled here, but does that mean it isn't an algorithm? Let's hear from the group who came up with this method. Group 1, do you think when you were using your method, you were following any steps? Oh, okay. So yeah, there actually were some steps here, but you wrote them all together in one sentence. But if we wanted to, we could add little notes to say that finding the areas is like step 1 and adding them up is like step 2. Yeah, I think that makes sense. So when we write algorithms, we don't always have to write them out as step 1, step 2, but maybe if we include that, it'll be easier for other people to follow our algorithms. That was good thinking, Sam. I think we agree that we were developing algorithms.
In this example, the coach helps students gain a deeper understanding of algorithms by pointing out and facilitating a conversation on whether or not algorithms need to have numbered steps. Let's watch one more example of the coach pointing out how students use abstraction to help them find the surface area of three-dimensional figures.
I know you're all working on finding the surface areas of these boxes, and I want to share a strategy I saw one group using to organize their work. So this group is using a table to write down information about the faces. So for each face, they're writing down its shape, its dimensions, and then also its area. So for example, for the bottom face of that rectangular prism, they wrote down that it's a rectangle and its dimensions are 4 centimeters by 5 centimeters, and then the area is 20 square centimeters. Now remember, we talked about tables as a way to use abstraction because tables show a lot of important information. So I wanted to ask this group why they were using a table. Why did you decide to make a table? Oh, I see. So you were having trouble keeping track of which faces you had found the area of and which ones you hadn't, and this helped you keep track? That makes sense. Oh, good point. So you also knew there were 6 faces altogether for the rectangular prism. So once you filled up your 6 rows, you knew how you had found all the areas. It's a great idea. What else did we say was helpful about a table? What's special about it? What's different about using a table versus, say, writing all your stuff, important information in a list? Yeah, the rows and columns can be really useful in a table, right? Because they show related information. So, like, what does each row show in this table? What does the information in a row have in common? Yeah, so all the information about one face is together in a row. What about the columns? Let's focus in on this last column. What's in that column? Yep, so all the areas of the faces are together in one column. And why is it useful to have all of those together? Yeah, so in this problem, we're actually trying to find the surface area of the whole box, not just the areas of the faces. So we have that last step of adding up all the areas of the faces. And so it's useful just to have them all lined up right here. Good abstraction strategy, group. Maybe some of the rest of you can use that strategy too.
As you plan to prompt and point out how students are using CT practices, consider these questions. What are some strategies my students could use to solve the problems in this lesson? How might a CT practice already be a part of or add to those strategies? How might I recognize when I see my students using a CT practice? And how might I identify when it would be helpful to prompt a student to use CT?